Okay, I think we can get started.
Yes.
Welcome everybody to the first American Physical Society topical group on the physics of climate seminar series. This is a seminar series we run the second or third Wednesday of every month during the academic year, and the purpose is to introduce physicists to problems in climate, either because they just want to learn about it, or because they're thinking, or perhaps because you're thinking of working in the area. And I can think of no better person to kick off this series today than Valerio Lucarini, who is currently the chair, I believe, of the topical group on the physics of climate. Valerio has been doing leading work in the application of non-equilibrium statistical mechanics to problems in climate. He is currently the professor of, I was just looking at your title, professor of applied math at the University of Leicester, from which before this he was professor at Reading and at Hamburg. Hamburg before that. He's a member of the Academia Europaea. He has a prize from the Society of Industrial and Applied Mathematics, Mathematics of Planet Earth. He was the Lorenz Lecturer for the American Geophysical Union and has the Richardson Medal from the European Geosciences Union and the Whitehead Prize from the London Mathematical Society. And I think without further ado, I will let him start. If you have questions during the talk, please drop them in. Please enter them into the chat. At the end of the talk, we will open for questions, and I will call on people who can ask questions verbally as well. So without further ado, I'll let Valerio take it away.
Thanks a lot for this opportunity. I'm glad to meet all of you guys, at least remotely. So let me share my slides, and let's see whether I manage to get things started. Yeah. Can you see my slides? Yes, good. So, okay. Today I'm gonna discuss some results we've been obtaining in recent years, trying to exactly develop, hopefully, a better understanding of climate change using response theory for non-equilibrium systems. In particular, I will cover two topics, one more, let's say, less extensively, one more extensively. One is how can we improve the interpretability of response formulas? So this goes beyond, let's say, the specific topic of climate by associating different components of response operators to specific modes of variability. So it's a problem of interpretability of the fluctuation dissipation theorem. And this would be achieved by basically combining response theory with the formalism of Koopman/Kolmogorov operator. The other part, which is more specific topical with climate, is how we can use response theory to basically provide solid foundations for detection and attribution of climate change. So, and I will present some very new results that show how we can literally construct the fingerprints that are needed for explaining observed climate change signals. So this work, of course, comes from the collaboration with many people, some of whom are mentioned in these first slides. So the climate as a starting point is a non-equilibrium system that is where the non-equilibrium conditions are set by the unequal absorption of solar radiation, and the entirety of the dynamics we see comes from the attempt of the system to establish an approximate non-equilibrium steady state. The climate, if we go to the phenomenology, is an incredibly complex phenomenology of a multi-scale system with no time-scale separation, and this is essentially what makes the construction of a theory of climate very hard, because it's very hard to separate what is slow from what is fast, because it's subjective and it's pretty much depends on the problem we're asking. And the other issue is that when we have a system with this such a broad band and messy spectrum, it's very hard to separate in a sort of a clear way signal from noise. Okay, in some sense, the multi-scale nature of climate tells you that the climate has always been changing. Doesn't mean that there is not a response of forcing or some sort of trend, not necessarily a linear one, that we can define rigorously. And that's actually the topic of the reason why we can use response theory to deal with this problem. If we go, of course, on an ultra long time scale, we discover probably the most fascinating aspect of climate, that is its metastable nature. And the importance of this feature is, cannot be overstated, because the transition between competing metastable state is basically the key ingredient that has led to the development of life as we know it. Climate has seen extended period of time under snowball. We know that this issue of multiple equilibria can be relevant for exoplanet as well. And if we consider smaller scale or shorter time scale, the manifestation of metastability that is particularly relevant today has to do with the occurrence of tipping points. So tipping points are in time what in a sort of a time domain, what metastability is in a configurational space. Okay, so this is makes, of course, the problem particularly interesting and fascinating. Indeed, we observe already from the records the full portfolio of behavior of the system, of our climate response to perturbation. We have regimes of smooth response. We have regime where we get close and have proximity with to critical transition. And then we have actually the manifestation of metastability, so the jumps through different mechanisms that I will not talk about today between competing states. Indeed, how can we make sense of this? And of course, something that has been incredibly, I would say, influential, intellectually stimulating, is the whole program of stochastic climate models proposed by Hasselmann, who posited that in order to construct the theory of climate, we basically have to separate in some form, fast from slow scales, define climate as the slow scales, and basically understand that noise in the form of fast fluctuation is integrated by the slow variable. So noise becomes something very important. Of course, as I mentioned, this is somehow in contradiction with what I said before, because we can't have this separation of scale. Nonetheless, this is a very good point. And this, I mean, it's fundamental, intelligent, and creative angle over which that can be quantitatively improved by considering how to do model reduction when we don't have time scale separation. But what creates the noise, and this is where the dynamics and geophysical fluid dynamics becomes so relevant, the noise comes, this is very important, the noise comes from the presence of variability on different scales due to dynamical instabilities. So there is no dichotomy between stochastic, of course, and deterministic chaos, as we know from contemporary probability theory. So the source of the noise is basically turbulence, broadly speaking. Now, all I mentioned is in this sort of, we can construct a theory of climate stochastic. If you want, as I said, from now on, we will pursue a stochastic angle of climate. That means we have an equation with noise, but, sadly enough, we live all in one realization of the world, that we don't have access to the multiverse of other, realization of climate. And my host today is an expert in multiverses. So unfortunately, we are grieving the lack of multiverses here, and we have one manifestation. So how do we reconcile one realization of a stochastic process with, as an example, a statement on the presence of a trend? This is extremely non-trivial from a very fundamental viewpoint, because signal, in a sense of response of a system to perturbation, is a statistical mechanical statement. But the signal that we see in one individual realization, in some sense, in a statistical mechanical angle, does not really exist. Who cares about the individual realization? Unfortunately, we live in this realization. So how can we link these two fundamentally different levels? How do we lift the statement on ensemble averages onto an individual trajectory? This is all the difficulty and the tension of attributing climate change to a forcing, okay? Now, to do what is the operation of detection and attribution of climate change, which is the fundamental building block of all the IPCC reporting. So we want first step one, we check the quality, we check a climate signal, say temperature signal, and we can make a statistical statement saying whether this signal is stationary or not. So this is just a detection of a, let's say, a variation with respect to some sort of reference state. But how do we do the attribution? So how do we link causally, and this is a very important keyword, enacting forcing onto the observed signal. So how, it's not only rejecting the null hypothesis of we are within climate variability, how do we link a forcing to a response? So this is, we will discuss this later, but this is very non-trivial. So, but what we know, to make a long story short, from a wealth of analysis of the last 20 plus years, is that one, climate change is real, so the climate change signal is not a fluke. And second, we have confidence that anthropogenic activities are responsible for such a signal. And the goal of my presentation today is try to convince you that how statistical physics makes these statements much stronger, okay? So let's do the first step. So let's first introduce the tools, the statistical physical tools we need to basically construct our theory. So first we will work in the world of statistical physics. So we will not have individual realization. It's only about ensemble averages. So what is our starting point? We start from a Langevin equation. So we have an equation in high-dimensional space where we have a drift term and a noise law, and we perturb this drift term and or the noise law with some small, in some sense, perturbation. So as we know, we can associate a Fokker-Planck equation to a Langevin equation, and we can expand, this is a very standard, we can study the correction of the measure due to the acting perturbation with respect to the invariant measure that is found in absence of perturbation. So there are classical perturbative methods to do this, and there are conditions that can be established ensuring the convergence of this perturbative approach. Anyway, so this we have, one can derive formulas for studying, for deriving exactly, answering the question, how does the invariant measure of the, how does the measure of the system change as a response, in response to this perturbation? But, you know, again, we don't don't have access to the measure. We are more interested in the change in the expectation value of observables. So we take an observable, any climatic quantity of interest, but could be, of course, you know, the same applies for any complex system you're interested in to describe by the Fokker-Planck equation. And you can write explicitly formulas describing the correction of the change in the expectation value, time t of your observable as a result of your time-dependent perturbation. So this is a general frame for response theory, which generalize the key and extremely important result by Kubo in the 1960s, and there's been a wealth of results also in standard textbooks explaining this. Now, the nice thing is that if the invariant measure of my system is smooth, which is the case for if our background is a stochastic system with suitable condition on the properties of noise, we can write the green functions as well known as a correlation between observables. So this is the essence of the fluctuation dissipation theorem. So response operators are correlations of suitably defined observables. So this is a rather general framework for the FDT, also far from equilibrium if we have noise. So remember, FDT can apply also in absence of detailed balance. Now, the question is, can we use this framework to do something helpful, useful for climate? So the idea is, what we can do is estimate the green function and then use this green function for our observable of interest to perform climate change prediction. So this has been attempted with success on models of different level of complexity. The easiest protocol to do this is to construct the green function by doing an instantaneous perturbation of your parameter of interest, derive the green function from that, and then use this green function to convolve your time modulation of choice for your parameters, and then perform predictions. So this is, let's say, a general protocol each time you have a response formula of this sort. And this formulation allows you to generalize the well-known concept in climate physics, like climate sensitivity, transient climate response. So we have you get explicit formulas for these very important climatic quantities, and you are able to have a magic tool that transforms forcings into response. So that's exactly the idea of a response operator. And in more abstract term, it allows you to construct the properties of the so-called pullback attractor. So the generalization of an attractor for a time-dependent system. Now, as I said, this as an example, we use it on a climate model of intermediate complexity to study the response of the global temperature, surface temperature, to change in CO2. But you can also convince yourself that if you define your observable in a suitable way, you can construct, as an example, the response of the spatial field of temperature, and still you obtain an extremely good agreement between what you get from response theory and what you get from a series of independent targeted simulations. So this approach based on linear response theory seems to work well in climate models, and things are somehow surprisingly successful even when you upscale your methodology to Earth system models of the CMIP class. So this is in particular, this study was done on models of the CMIP 6 class, so Earth system model that basically are part of the latest IPCC report. So in this case, one can find that using response theory, you are able to capture critical aspects of climate change, like the occurrence of the cold blob in the North Atlantic due to the competing effect of slowing down of the AMOC and increasing overall surface temperature. You get a clear signature of the rapid decrease of the AMOC and of the Antarctic circumpolar current. And you see how the AMOC is much more sensitive than the Antarctic circumpolar current to CO2 increase. So, this thing has a huge, very good quantitative ability to perform climate change projection. And of course, the important thing is that once you establish the validity of a linear setting, a linear response operator, you have a continuum. You have the ability to perform a continuum of projection depending on the forcing you apply. So now, this is a sort of top-down approach. But the question that one might wonder is, okay, you are able to construct this green function, but what do I really learn about the system? So, you basically told me how to construct a magic box, and I should believe you that it works, so that you throw inside in the box a forcing, and I get as output the response. Okay, so what? Is there something more to learn? So more recently, some colleagues tried a different approach from an empirical basis. Actually, this is also, some of these ideas were already present in early papers by Hasselmann himself. So what about writing the green function as a sum of exponentials with different time scales? So Mendonça and Torres Mendonça and others, and from a slightly different angle, Bastiansen and others proposed to construct a surrogate empirical green function as a sum of exponential, where of course the inverse of the lambdas describe my time scales of interest. So I'm trying to deconvolve the green function in terms of different time scales. So this was partially successful, even if the conditions in this implementation, they imposed that lambdas were real. So not allowing basically for true non-equilibrium phenomenon. So now, this was quite interesting, is it possible instead to do this decomposition? Is it possible really to write this decomposition of a green function as a sum of exponentials? And if so, what do I learn about the system? So in order to do that, the strategy that we followed was trying to use some recent, I mean, even if the idea itself is not so recent, but recent, let's say, revivals of some idea of dynamical system use it to expand response, to supplement response theory. So the idea is to take the angle of the basically Kolmogorov operator formalism to study the evolution of a system. So instead of studying the evolution of the state of the system, the orbit of a system, you study the evolution of observables. And you can easily convince yourself that the evolution of observable follows a linear evolution, but in an infinite dimensional space. So in some sense, once you have your observable, you can decompose it in a sum, as a weighted sum of eigenvalues and, eigenvectors of this evolution operator. So this is the essential argument. So somehow you are taking a functional analytical approach to the problem that really resembles a lot the formalism of quantum mechanics. What you learn from this? Once you take let's look at this green function, which is exactly, let's say, the fluctuation dissipation formulation. So I have that my green function is written as on top, there is an evolution at time t of an observable 5, 0, of an observable evaluated over the unperturbed dynamics. Then I use by integration by part, and I write my green function as a correlation between my observable at time t and another observable. That's exactly the FTT. Now, what I do is write this evolution operator as sum basically I do a spectral decomposition on the eigenvalues and eigenvectors of the evolution operator itself. So by doing this, it's the exact equivalent of doing an expansion in eigenvalues and eigenvectors of the Hamiltonian operator in quantum mechanics. So the result of this is that suddenly I break down this, I expand this expression into an infinite sum of terms under suitable hypothesis. I'm not going to go into these technical aspects, which allow me indeed to write in general the green function as a sum of exponential terms, whereby the factors in the exponents do not depend on the observable and do not depend on the forcing, and the coefficient depend on the observable and the forcing. So the lambdas are fundamental properties of my system. So basically, I reach a level of interpretability of the response operators, going from just a generic link between forced and free fluctuation to the possibility of itemizing my response, the contribution to the response into what comes from each mode of variability. So this is really, I believe, a step forward in improving our ability to understand the fluctuation dissipation theorem and linking forced and free fluctuations. So this is, among the various side effects, allow us to understand, to write explicit expression for general correlation functions that were first proposed by Michael Shekroun, and to write, as I said, response operators as in terms of, so once I know my Koopman modes and the shape of my forcing, I can write my green functions for any observable and any forcing. So it gives me predictive power. So I'm able to link what I observe from the unperturbed system to the response to a generic perturbation for a generic observable. So I make, I think, a leap forward in my understanding of the sensitivity of the system. So this is, and this we have tested this, there is a recent preprint on this on arXiv on simple systems. So this is, but the framework seems to stay strong. Another property, quality that we learn from this, that will become useful at the end also of this presentation, is that we have a general framework for understanding the occurrence of tipping points. So the tipping points occur when the so-called spectral gap, that is the rate of decay of the slowest decaying modes, closes to zero. So we have a exactly that these three things come together: the divergence of the response of a generic response operator, this critical slowing down of the decorrelations, and the closure of the gap. So the combining response theory and Koopman formalism, we have explicit expression for a generic tipping point. Basically, you are able to create a general equivalent of the classical qualitative landscape picture of tipping point that you see in the left of this slide. Okay, so this is a condition of criticality. Now, okay, so this is the general framework of response theory that it's useful for our goals. So now let's go. So far we are living in the sort of a Platonic world of statistical mechanics, even if it's a messy world of non-equilibrium, because we live in ensemble averages. So I have not committed myself to any individual trajectory. Everything is expectation value of expectation values of expectation values, and so on. But we don't live in an expectation value. So how do we make, and this has taken me a very long time to understand this, to be honest. I have really hard time to relate the statistical mechanical statements to what happens in the real world. So how do we make this result relevant for a specific problem of climate change signal we observe? So detection and attribution, as I said, tries as the goal of relating a forcing to an individual trajectory of the climate system. This is a very non-trivial task. How and what is the end result of how does this work in let's say in qualitative terms? I have my climate change signal. I try to reproduce the effect of individual acting forcing, so increasing the CO2, changing the land surface, changing the solar irradiance, and so on. I try to see how these forcings sum up and compound themselves. What is the best way to compound this forcing to replicate as well as possible the observed signal? But of course, each observed signal is impacted by the natural variabilities, because this is a very noisy system. So of course, the problem is that each statement on detection and attribution is statistical in nature, okay? And the final result, if you look at this, is taken from one of the earlier IPCC report, but the message is this. There is a factor, usually referred to as beta, which is called the scaling or weighting factor, that tells you how much your forcing impacts the observed signal. And in the detection and attribution literature, you want this beta factor to basically be bounded away from zero, because if it touches zero, it means that forcing is not seen in the record, in the signal, and is centered around 1. So this is the idea. So that you want that forcing counts as with a factor 1 with respect to the observed signal. So now let's try to make this a little more formal, and then we will try to understand why this is the case. So the optimal fingerprinting, and again, this is an idea due to Klaus Hasselmann, amounts to this. Let's have a signal YK, which is a climate signal, can be a spatial fields of, say, decadal averages, decadal anomalies in the temperature. And I want to reconstruct this sigma, I want to find the optimal reconstruction in terms of the betas of this signal as a weighted sum of my XM, which are my fingerprints, so the response of my system to perturbations, a big M of this signal, plus a natural variability. So remember, XM are the fingerprints and are constructed as ensemble averages of model response to individual forcing. So I take a model, I have a reference state, I apply the forcing, I repeat this many times, I get an average signal of the force. So this is it's a quantity that lives in the ensemble averages, whereas Y is a quantity that lives in the individual trajectory. So there must be a natural variability that is this RK which links the two. So remember, optimal fingerprinting always relies on model, that is XM tilde, and signal, observed signal, that is the YK. So there is always, it's always a model and matching data and model. This is very important, okay? Now, again, as I said, the fingerprints are constructed from one or more models by doing the operation I mentioned. I have a reference climate state, I apply that individual forcing, I observe the change, I average over many model runs, and I get my signal. Okay, that's with the fingerprint. Now, the key ingredient of detection and attribution is the element of causality. So the whole idea is that you want to causally attribute the signal to this combination of forcings. And the causality is intended in the Judea-Pearl's strong sense, because this is what implies, in some sense, legal responsibility for those who create the signal. So it is about comparing the factual world with the counterfactual world, where the actual world, where we live in, with the counterfactual world, where each of these forcing is applied separately or not applied at all, which is the null hypothesis, basically. Of course, we have only access to one world, the one we live in, but our best approximation of the counterfactual world is performed with climate models. So again, we see how important climate models are in this, okay? Keep in mind, this is the so-called interventionist approach. So we change the world by applying selectively this forcing and all this forcing together in our real world. If you don't have the so-called interventions, you have a much weaker sense of causality in the so-called grandeur sense. So this, it's important. You have to apply selectively these forcings. Now, there are solutions to this problem in simpler or more complex statistical hypotheses, always bound to very strong hypotheses on the properties of the natural variability, usually assumed to be a Gaussian random vectors with a given covariance matrix, and you get an explicit formula in the simpler case, or a more convoluted formulas in a slightly more general case for the betas. So you give me the signal, you give me the fingerprints, you give me the properties of the correlation matrix describing the natural variability, and they give you the betas. Okay. And the betas, once you do this operation on a field, you are able to reconstruct, to decompose the temperature signal in the various, this is magic, in the various contributions coming from the various forces. This is the magic of detection and attribution. And then you can do, you can attribute the observed trends by saying we observe a change, I don't know, a temperature change of 1.5 degrees. 1 degree is due to anthropogenic activities, 0.5 is due to this, and so on and so forth. Look at this graph where you have indeed this circle of uncertainty, which is very close to the point .11. Okay, we come back to this here. So now, coming to the end, how does linear response theory lead us? So far, that's very important. Detection and attribution equation, the detection and attribution equations have been proposed as a purely empirical approach. Okay, so the idea is that I sum linearly these fingerprints and I try to reconstruct the signal. So it's a problem of linear regression defined on purely statistical grounds. So the goal here is, can we use a more fundamental theory, a statistical mechanical theory, to derive something that looks like the detection and the optimal fingerprinting equations, and possibly propose some extensions. So that's what we're going to do in this final part of the presentation. So we go back to our response formula. So this is the perturbed dynamics. We add a certain number of forcings, both to the large-scale fields or to the noise, which would be small-scale forcings. And of course, we end up that with the fact that for any observable phi, we have that the correction with respect to the reference state phi 0 is given by the sum of contributions, different contributions, each coming from one of these forcing. So let's plug all these acting forcing together up to a number m, and we have at the lower, you look in the lower graph, the lower equation, you have that the anomaly at time t, which will be my signal, is given by the sum of m terms. So this is, but remember, this is, we are still in statistical mechanics. So we live in the world of ensemble averages. So this is the ensemble average on the pullback attractor at time t minus the reference ensemble average is equal to these terms. Now, if we lift this result to the individual trajectory, we get this result. So basically, we add an element, we choose one realization in the pullback attractor, and we get that the actual signal, y of t, so the difference between what we measure for this realization of the stochastic process minus the ensemble average is equal to what? To the sum of these fingerprints plus the natural variability, which is again left on the right-hand side. So somehow, by basically adding the natural variability, we obtain something that looks a lot like the optimal fingerprinting equation, except for the betas. And why? And this is one thing. And the reason why the beta does not appear exactly because we are using a linear response theory. So these betas, in absence of biases, if we are within linear response approximation, would be by definition equal to 1. So the betas are basically, the fact that the beta should be constrained around 1 is exactly a result of the linearity of the approach, which again is the starting point of the optimal fingerprinting method. So here we derive this stuff. Now, important thing, we learn a lot from this, because here the natural variability is not that we derive from the equations, is not the natural variability of the unperturbed climate, which is how things are cast in the optimal fingerprinting method, that is the variability in the pullback attractor, which has a correction with respect to the reference state. So we have a new notion of natural variability, which applies for time-dependent systems. And now the question is, does this thing work? Okay, so far, so what? So now you have derived these equations. You have shown me how to go from take a linear response theory, do some sort of manipulation, and derive the optimal fingerprinting. And again, a good question is, who cares? So what is this relevant? So now, why is this relevant? Is because I'm able to construct the fingerprints once I know the green function. So once I have the green function, I can compute the fingerprints for any pattern of forcing. So I have infinitely more power in constructing, in doing my climate change detection and attribution for any scenario you give me. So the idea is does this work? So we tried this, and these are very new results on two different climate models. One is a simple but incredibly very relevant energy balance model, the Gilseller's 1976 model, and then on an actual coupled GCM. So this is the energy Gilseller's model. I don't need to introduce it. Describes absorption, energy absorption, diffusion, and emission for a latitudinal, longitudinal band. So what we do is there are lots of parameters in this model. One parameter describes the greenhouse effect, so the gray nature of the atmosphere. And we have added the second forcing. So we have altered this parameter trying to describe CO2 increase. And then we added a local decrease in the incoming solar radiation in the northern mid-latitudes to describe the impact of area. So it's just as a thought experiment. So we have combined these two and constructed the fingerprints using response theory and tried to use these fingerprints to do detection and attribution at different time horizons for this model. So we have some runs of this model, which are done with the full forcing. We construct the fingerprints using response theory, and we try to use these fingerprints to do detection and attribution of climate change. And the results are very fascinating, because what we get is that as the forcing becomes stronger and stronger, the confidence in the detection and in the of course, we have detection of climate change, and we are able to find consistently attribution of climate change to the CO2 forcing and to the aerosol forcing. So we are able to separate the two signals, even if one, the CO2 forcing, is much stronger and totally different spatially than the aerosol one. So, and what we see in our applied choice, the aerosol forcing decays after a while because it wants to represent a sort of pseudo-realistic sort of time development of pollution. And what we see is that when time goes on, the aerosol forcing becomes irrelevant. And so then the attribution becomes harder again. So somehow we are able to follow the statistical quality of the attribution in time. So in other terms, the theory works. Second step, much more challenging. And so, and this, the detection and attribution is done on the full temperature field. So this is very important. We try to do the detection and attribution over all the latitudinal temperature profile. So that we are exactly mimicking the protocol of detection and attribution in this low resolution, of course, very low resolution model. The same is repeated now for instead a coupled GCM. So this is a PLASM coupled with the LSG, with an ocean model. So this is a coupled atmosphere ocean model, a simple one, still an actual good climate model. And what we do here is we only perform CO2 increase, and we compute through the green function formalism I showed you before, my response operator, and I try to repeat the experiment as before. So this model is relatively simple, has only 10 to the 5, 10 to the 6 degrees of freedom, but it has a lot of, has a nice climate sensitivity of 3 degrees, reproduces the property of the cold blob, just like the much more complex Earth system model I mentioned before, and it does it for the right reason, because of the slowdown of the circulation. So this is a pretty good climate model. And for this climate model, we see that response theory works very well to perform climate change prediction. So, you know, the statistical mechanics supports us. But remember, we are doing a different experiment. We want to do detection and attribution. So this is a necessary condition for detection and attribution to work, not a sufficient condition. What we do is then use the response theory to compute the fingerprints, and use these fingerprints to do detection on the attribution of climate change on the full temperature spatial field, so 2048 variables at the same time. And we are able to find, you see this blue line with the betas, we find an extremely convincing ability to attribute climate change to CO2. Of course, here we are using we are in the perfect model scenario, but we exactly show that the climate, that we are able to use the fingerprints constructed with response theory to perform detection and attribution. So we confirm that the statistical mechanical theory behind detection and attribution justify the equations that have been used so far in an empirical manner on a complex climate model. So this is not a toy model. This is an actual climate model. Now, so what we learn, as I said, is that we understand why, in the first place, we can write these linear regression problem. We understand much more the nature of variability. There is a link between the causality à la pair with the causality of the green functions. This is an interesting aspect. And there are many other aspects to one can infer, and we can use this framework to perform. This has not been done yet. Detection and attribution, not on the change of climatic observables, but change on climatic correlations. So we are able to, we should be able to address the question of how does climate impact climate variability? So the next order in statistical terms. And, well, I'll stop here. Thank you. Oops.
Thank you. Thanks for a great talk. That was really wonderful. Are there any questions from the audience? I'll wait for a second. Please, you can raise your hand and I can unmute you if you want. If not, I have some questions. Yes, Francesco Fedele. Should be allowed to talk. Yeah, there we go.
Yeah. Hi.
Hello? Yeah, you need to unmute.
I wrote the question on the chat.
Oh, I see. I see it.
I don't.
Oh, Valerio, how are you?
I'm good. Hi.
Francesco. Francesco.
Yes.
Hi, do you want to just tell
Yeah,
Steve
just
yeah,
just
let
go
us know
ahead
what your
with the
is.
question. Yeah.
Say it again?
Can you just tell them your question directly?
Okay, yes. I am in a public space, so I'm in a
see.
shop.
We can see, we can hear you very well. I have a train nearby, so don't worry.
Okay, yeah, okay. No, I know, but I'm pretty loud, so I don't want to bother people around me. But the question is, I know that the Koopman operator is at the joint of the Perron-Frobenius operator.
Yes.
And
yes.
usually these operators are non-normal. I think the climate system is a non-normal flow. So basically, they are sensitivities to the to small perturbation in the base flow. And so and that's why, for example, Trefethen come up with the idea of pseudospectra. And this is very typical in these are the problems I've been encountering in transition to turbulence when they try to understand. And so basically, then there is also this non-normality. It also imply that the most observable mode do not coincide with the most reachable modes. So it looks to me that your approach using response theory is a generalization of these approaches. And so I wonder if how do you do you have sensitivities of the eigenvalues? And if you do, how do you handle that?
No, okay. So the important thing is here, I am not so the main of the problem you describe is very important to be clear, but emerge when you're trying to follow a trajectory. Okay. So when you're trying to follow a trajectory, so if you want to use this Koopman operator to basically predict the evolution, you might, slightly make a mistake and then go totally astray for the reason you're describing. So the robustness is problematic. Here, I'm using that expansion to construct to perform statistical statements. Okay, so it's different. I'm using here, to be clear, the Kolmogorov version. So in the stochastic Koopman operator. So basically, I'm using these as a base to expand my observable. So it's a bit different. So formally, it looks similar, but I'm not following a trajectory. I'm using it then to do an ensemble average. Okay. So what I can tell you is this expansion that we have now a preprint just out since a week on arXiv. I'm very happy if you give a look. First author is Zalje with Igor Mesic and other collaborators, where we tried this on some maps, simple models yet, but the results are extremely good. So you basically break down the green function that in that case are very easy to be computed into the sum of all these contributions, which are very non-trivial. And in that, I agree with you. It's definitely not true that, as an example, the slowest mode is the one that's going to contribute the most to a generic forcing observable pair. So the intuition that what is big is going to contribute the most is wrong. Okay, and this is, if you want, another clear manifestation of non-equilibrium. Okay, so it comes, if you want, on a climatic sort of nuance There's a famous paper of Ed Lorenz in the, I think, 1980, saying that when you have multi-scale dynamics, the derivatives can be written on the components that are very small in terms of variance. So it shouldn't come to a surprise, really. So yes, we do find these things anyway.
Okay, thank you very much. That was very clear. Thank you.
Thank you.
Are there other questions from the audience? If not, I think I have one. So
Please.
at
Yeah.
the end of your the first part of your in the first part of your talk, you're talking about evolving these averages forward using using some evolution operator. Is that the first is sort of a formal question. Can I associate to this some sort of a similar, like a path integral kind of average, like Onslauger-Machlup or Martin-Zidji-Rose or whatever?
So sorry, in the here you mean?
Yeah, I mean you have a way of evolving these forward in time, the averages forward in time. You do what look like a path average. So I'm wondering.
So
yeah, right here. Got that one.
Yes, yeah. You do so the idea is it's really it's really more of a formal definition of what is a linear operator somehow. So the idea is you are able to go. So originally the Koopman operator is on a deterministic setting, and this is where it's quite. I mean, that is more intuitive understanding of it. Now you can construct it, formally using an adjoint formulation. Okay. Now the idea is, if you look at measures, you want to use the Perron-Frobenius, Ruel-Perron-Frobenius operator and corrections thereof. If you want to look at observables, now you have these stochastic Kolmogorov operators. So at the end, you always, and this is very important, you're always going to take, as you suggest, expectation value over all realization of the noise. So that's very important. So that's what this is, if you want, the beauty or the luck, but it's also the limit, because it's always a statement on average, ensemble averages and expectation values. We like this. We love this. This is beautiful, right? But this was the major step that together, in fact, the contribution of this second part of the work comes with my collaboration with Michael Shekrun. So the big, what I honestly think is quite a big step has been to go from this to individual trajectories, and so go, if you want, for statement in probability to statistical inference. Statistical inference is how you link what you observe to a universe of possibles. Okay. Yeah. So, and this is exactly how you do. So once at a certain point you add, okay, I'm selecting an element of this object, which I don't know what it is. And then the best I can do is to make statistical statements once I observe it. So this is this is, if you want, the rupture between the theory and the empirical approach. But what I like is that you derive the empirical approach from the theory.
Okay. Maybe a slightly different question. A little bit later, you talk about identifying turning points by the collapse of these. Shrinking of the gaps in these eigenvalues, and it's sort of, when I see that sort of shrinking of a gap, I use, at least in sort of an analog, say, quantum problem, I think of a symmetry breaking transition or a glass transition of some kind. I'm wondering if this is related to
no, okay, you have that, okay, it's, okay, if you go to a system, but in different class of system, that's a kind of work I've done with Zagli and Pavliotis. So if you take, as an example, a multi-agent system, you have different classes of critical behavior. One is similar to this, and one is really the phase transitions. So then you go more into, as an example, a synchronization transition. You can describe with a similar angle, but you have other effects. Here, it's actually, you don't need to go through that phenomena. So you basically have that the system, let me try to find here, that the system, if, in some cases, if you change a parameter or you add a forcing, the spectral gap goes to 0. So now the key thing here is that, let me find the general equation here. And this is in frequency, because, you know, I have my perversions, so I come from the condensate matter, so I like frequencies, I don't like time. So the susceptibility of the system ends up, and this is, I like it as a sort of a classical quantum chaos link. So the susceptibility of this generic system, stochastic system, is the sum of some harmonic oscillators. Very boring, like physics is boring. And so is the co-spectrum of generic observables. So now the thing is, the alphas, which would be the dipole momentum in optics, become these terms. The lambdas become the basically energy, the equivalent of the energy jumps in quantum mechanics, but they have a real component because thing decays. So you have a, you know, there is a nice equivalent with what happens in optical cavities as an example of things like this. But the formula is very similar. But the good thing is that these two formulas are identical except for the alphas and betas. So the condition of criticality is universal and comes from when the real part of these lambdas goes to 0. So if when the real part of one lambda goes to 0, if its imaginary part is 0, you have a static. You have a static sort of tipping point. If the imaginary part is different from 0, then you get a rotation. So you have a sort of a generalized bifurcation in very high dimension. And this is the kind of phenomena we see in climate that then we like to interpret as unstable, unstable periodic orbit, you know, some sort of unstable cycle. But it's not an unstable cycle. It's a case like this where in the condition of criticality, the imaginary part of lambda is non-zero. So things rotate somehow in very high dimension. So this is why I like this sort of general setting. Yeah.
Right. Good. Thank you. We have another question from Balan Nadiga.
Yeah.
And make sure you need to unmute.
Yep.
Hey, can you hear me?
Yeah.
Yes, very well. Yes, thank you.
Hey, Valerio, very nice synthesis of a lot of things, in particular the fluctuation dissipation theorem and the Koopman, stochastic Koopman kind of approach. So my question is, I missed a lot of your talk. I only caught the last 15 or 20 minutes. But I'm wondering if this approach, with this approach, can you say anything about predictions, either in the statistical sense or in the trajectory-wise sense? And have you done right? Detection and attribution is good, but what about in the prediction sense?
So no, the prediction has been the starting point. So of course I'm talking about prediction of a model with model. So what is the prediction? The prediction in my sense is that I compute the green function on one specific protocol of forcing, and then I use it to predict the response of the system to different protocols of forcing. Okay, so that's the prediction in that sense.
Okay, but is it purely in the linear sense, or I mean, if you had to consider the non-linearities of the system? So I suppose you're talking about it in the FDT sense, right? In a small perturbation, evolution
but
of a small
is big, but it's small in this kind is big. So as an example, within 2 times CO2, the response of many quantities in the climate system is surprisingly linear. Linear in this sense. Of course, it's not in the sense that you just scale things, because you will, in the sense that there is a response operator. So, you know, things will scale differently depending on the time scale of the forcing. That's the whole idea of susceptibility. But you have an overall linearity on different classes of forcing, which works very well. So of course you have then nonlinear effects, but as an example, I give you a specific example, the cold blob is not a nonlinear effect, it's a very linear effect. It's totally linear. It's just you can construct it with a linear operator, it works extremely well. Similarly, the strong reduction of the AMOC, it's a very linear behavior. It's
No,
just a
I agree completely with you, right? In particular, the cold blob, you can even just do correlational analysis, linear correlational analysis, and see its behavior. Okay.
But of course, then things start to become, as an example, if you had, let's put it this way. So, first, you can in principle go beyond linear response theory. It's possible.
Okay. Yeah, that's what I was interested in.
It's absolutely possible. So this is very important. It's possible and formally possible, mathematically possible, and computationally possible to do that. This just, comes after. You can write equations. In fact, in this more recent paper with Michael, we wrote also how you can do fingerprintings with no linear effects. It's possible to do all of this stuff. Now, the response, there are methods, standard methods used to separate linear and nonlinear components. You just have to do some playing with the intensity of the perturbations, but it's definitely possible. And so truth of the matter is you seem to have, in the case of climate, it's not a general case, a relatively large range of linear response. So this is, goes against the intuition. Since the system is very nonlinear, there can be no notion of linear response. This is a totally wrong statement.
I do agree.
I know you know. Just wanted to underline this. So the fact is that for some reason, the range of linear response of the system is quite big. Now, of course, once you get close to a tipping point, things will change. Okay, but the good thing is that this is very important. Linear response theory will tell you where the tipping point is. Accurate quantitative prediction near the tipping point will require nonlinear terms. So that's two separate things. So the condition of tipping is written in the linear perturbation equation. If I'm close to tipping and I give you a forcing of finite intensity epsilon1, to give a good prediction, I might need higher order terms because the sensitivity is very large. Okay, that's it.
Okay, yeah, so sorry, just a quick follow-up, right?
Yeah,
sure. I do not fully understand this prediction of the tipping point. I mean, it seems more ad hoc to me, but setting that aside, just like you leverage your approaches to detecting and detection and attribution in a trajectory-wise sense.
Yes.
Have you thought of prediction in a trajectory-wise sense, leveraging your previous the linear FDT?
So the prediction, the prediction in a pathwise sense, of course, you can do it only in a deterministic setting, not in a stochastic setting. There is no concept of course, of prediction there. And of course, people, this is not something I have done. So people have used, and I think also have used the Koopman formalism to do prediction.
Oh,
yeah.
Okay. Okay.
So the idea is that one could try.
I was mainly thinking of the analogy that you had, or the application of FDT and Koopmanism in the detection and attribution.
Right? I mean, honestly, no. So the problem is FDT works in an ensemble sense. So if you give me a forcing, I'm able to tell you the ensemble average of the response. So that's what it can do. Now, of course, it gives you a good guess, if you want, of the response. The nice thing is that what is the last part of the presentation, the one you have seen, is that this sort of reference response that you get through the FDT, and remember, this applies at each time horizon, is the background you use to then perform your inference of detection and attribution. It tells you around what the detection and attribution will take place. What it tells you, if you want, your zero hypothesis under the condition of existence of the forcing. That's why it's useful. Okay, so that's why. Yeah, that's now the prediction of the response for an individual trajectory. I don't think it's something that you can so easily do. Probably you can as time goes by, you can get some priors, you know, of whether you are on some sort of upper or lower quantile of the range of the response. But that's not something I've thought about, to be honest.
Okay, great. Thank you very much. Yeah, it'll
Thank
be
you, Balot.
fun to
Thank
talk
you.
further. Yeah.
Thank you. Yeah.
Any further questions? If not, let's all thank thank Valerio for a beautiful talk.
Thank you. Thank you very much.
And thank you myself. That was great. On the 13th, we will have the next summit. Summit is on the 13th. You can go to the APS GPC webpage to register. We are planning to have representatives from physical review letters
Yes.
who will talk about their their desire to get some papers on climate.
Yes.
So that should be lots of
So-
fun. So people, please show up for that.
Yes, so as a editor of PRE and also involved in PRL, I really encourage people to show up. There is a lot of interest and a lot of really good papers on climate that have come out recently in the APS journals. I think there is a really good momentum. And
Excellent.
it's a good opportunity, I think, to go in this direction. I mean, really, there's been some fantastic contribution in PRL, PhysRev X, PhysRev Research, PhysRev E, of course. So I think it's a good time to do this.
Indeed.
Okay. Yeah. Thanks.
Great. Thank you very much, Valerio. We'll talk to you
Thank you
soon.
very much. Bye-bye.
Cheers.
Bye.